In this video, you will learn how compaction is determined, specified, achieved, and measured. A good starting question is, why is this topic of soil compaction important to me? And the single huge answer is that structural failures can result unless soils are properly compacted. How is compaction defined? Compaction is a process to increase the strength of soil by increasing its density, which is expressed in terms of pounds per cubic foot. So compaction is necessary because engineers in the design of foundation systems need to base their design work on some uniform soil bearing value. A bearing value that the site development contractor must achieve by the proper compaction of the soils. In order to understand how compaction is achieved, let's review the composition of soil. As you may have learned in another one of these videos, soil is a matrix of three constituents: solids or soil grains, air, and water, in some combination which is illustrated here. Sometimes a phase model is also helpful. The non-soil spaces in the matrix are known as the void spaces, and that space is filled with air and water in some combination. Since the goal of compaction is to make the soil heavier, more dense, we need to be aware of the weights of these three constituents. You may remember the concept of specific gravity from high school. It is simply the comparison of the unit weight of something to the unit weight of water. So as we see here, air has no appreciable weight, and soil particles are about 2.6 times heavier than a like volume of water. This has an implication in the context of what is in the void space. Now keep in mind that soil grains are nothing more than very small pieces of rock, and they are not reduced in size by the compaction process. The process of compacting is about reducing the size of the void space by realigning the soil grains into a more dense arrangement and filling that remaining space with the heaviest possible material of our three constituents. Since not all possible void space can be eliminated, the second best alternative after grain realignment is to fill that remaining space with water. So to answer the question again, compaction is accomplished by applying energy to the soils with heavy equipment to realign the soil grains in a more tightly packed pattern, and by adding just enough water to fill the remaining void spaces. Now that we have some understanding of how compaction is achieved, let's understand how it is measured. There are standardized ASTM tests used to determine the maximum, that is the theoretical, density of any soil type. As you see, the history of this test goes back to the 1930s, and the test is named after its inventor, Ralph Proctor. Proctor's work identified the important role that water plays in the compaction process. Let's drop back in our discussion again to the three constituents of soil for a minute. We understand that after grain realignment we need to fill the remaining void space with water for maximum density, right? But the key point here is that since water doesn't compress, if we have too much water, it will displace soil grains and make the soil less dense. Remember, the specific gravity of water is 1 and of soil is 2.6. This is pretty neat. If we don't have enough water, the soil will be less dense than it could be, and if we have too much water, the soil will also be less dense than it could be. What this illustrates is that there is a direct relationship between soil moisture and soil compaction. In fact, another name for the Proctor is the moisture density curve. Let's explore the idea of the moisture density curve a little further. Just a quick recap. We understand how water is better than air in the compacted soil's void space. A second benefit of the water is that it acts as a lubricant as we apply the compactive energy needed to realign the grains. Okay, now to the concept of the curve. We said soil compaction is a process of increasing the density or unit weight. So on the left we see a simple graph with density and moisture content as the two axes. On the right is the equipment used to run the Proctor test. What happens is the mold is weighed empty and then the collar is attached. A fairly dry sample of soil is placed into the mold in 3 separate layers, and each layer is compacted with 25 blows from the drop hammer. After all material is in the mold, the collar is removed, the soil is trimmed off, and the filled mold is then weighed. After weighing, a small sample of the soil is removed and tested to determine the percent moisture in the soil. The corrected dry weight of the soil in the mold is then plotted on the graph, represented by this red X, say at about 97 pounds and 4% moisture. The soil from the mold is then mixed with a little more water, and the process is repeated, and another point is added to the graph. Notice that this point, because of the additional water, has a higher density. The process is repeated a third time with the addition of even more water, and another point is plotted, which is still heavier than the earlier plots. Again, the process is repeated a fourth time with even more water added, and the next point is plotted. However, notice what happened this time. Why did the last plot weigh slightly less than the previous one? The answer is the higher percentage of water has now started to displace soil grains. So we just traded soil at a specific gravity of 6 for water at a specific gravity of 1. Okay, probably 1 or 2 more molds are made with more water added and the points plotted. Then the points are connected, and we have our Proctor or moisture density curve. The curve clearly indicates the relationship between moisture content and density, but only for this particular soil sample tested. Let's learn 2 more terms in regard to soil compaction. If we plot a horizontal line from the very top of the curve like this, we call that value, which is about 130 pounds of cubic foot in this case, the maximum dry density. In other words, this is our theoretical maximum density for that soil under the Proctor test. Next, if we plot a vertical line down from the very top of the curve to intersect the moisture content axis, we find what is called the optimum moisture content. This is the best combination of soil and water to achieve the maximum dry density and therefore the strongest compacted soil. A good way to help remember the importance of moisture in soil compaction is to think of the 2 sides of the curve divided by the optimum moisture content line. The left side is called the dry side because the soil needs more water to achieve its highest density. And the right side is called the wet side since the soils here have more moisture than needed. Now let's understand how compaction is actually specified. Quick recap of our example tells us that the maximum dry density for our soil is 130 pounds a foot and the optimum moisture content is 13%. Okay, so when compaction is specified in our contract documents, it will be in terms of some percentage of the maximum dry density. For example, say 95%. This tells us, and the inspector who will be testing the compaction work, that the soil must have an in-place density of at least 123.5 pounds a cubic foot. If we plot that minimum value as the blue line here, we have defined an envelope where any field compaction test must plot in order to be passing, that is, above the blue line. And if we extend the lines perpendicular, we can quickly see that our soil moisture content must be between 9 and 17% for the test to pass. Let's take a look quickly at how field compaction is measured. On any project, the compaction of the soil will be measured as each layer or lift is placed and compacted. The usual method is to take 1 test per lift per 5,000 foot of area. Subsequent lifts are not allowed to be placed until a passing test is obtained in each area. If a test fails, the contractor must adjust the moisture content and/or apply additional compactive energy. In terms of field testing, the nuclear device is most universally used since it only takes a couple minutes to get the results. Illustrated here, then, we see examples of 2 tests that are taken, 1 test above the line, passing, and the other test below the line, which would be a failure.